Welcome to today's webinar, which is another webinar in the 3D Bridge module in FEM-Design. And my name is Alfred, bridge engineer and product owner of the 3D Bridge module. I work at StruSoft, who are providing the FEM-Design software. I'm sitting in Gothenburg, Sweden. And this webinar will be similar to the previous one. So if you attended that one, this will be familiar to you. The agenda for today is to introduce some more of the features of the 3D Bridge module. I will this time jump into one example, which is how to create some train loads for a bridge model, and then I will dive into this a bit more advanced topic, that is sensitivity analysis. But since what bridge engineers know, the time can be essential for our complicated analyses. So if we can reduce our time while maintaining some good results, that is really key. So I will show you how we can do this in 3D Bridge. And just as last time, I will not go into a lot of the really basic knowledge in FEM-Design, such as geometry modeling. I will not go into combination of loads, how we can group them, and not so much about results as well. So quite hands-on 3D module stuff. So with that said, or actually, just to mention this so that it's really clear, anybody who are in this call will get the recording afterwards, and you don't, even if you're not here right now, you will get the recording afterwards, of course. If you have any questions, please write them in chat. I will probably, just as last time, just get going to get as much as information as possible into this hour. So probably not answering a lot of questions, but please write them, and I can get back to you or write a summary in that same email, for example. So let's jump into this model then that I prepared. So we have a simple slab plus beam setup. I have some supports, two fixed supports here in the middle, two simply supported points on each side. There's a bit of asymmetry going here, which I think will make the results a bit more interesting. So with some of the modeling out of the way, we can jump into the load tab. Actually, I should start from scratch here. So this is, okay, the first tutorial is how to erase loads that you already created, which can actually be a bit tricky. You have to start to erase the load in the corresponding load tab. And once you've done that, then you can go into these grid patterns that are generated, and then you can erase those, because you cannot erase these patterns as long as you have a load in your model. So now we can see our load list is empty again. Okay, so we start from this testing load case. We go up into the traffic load tab. And since we're going to be doing some train loads, we have to go by this train option. So not the roadway option that I've been working through earlier. And now we have two options, either a simple line model or a railway model. And this is a similar setup as for the road alternatives, meaning that simple line model, this is just a straight line that you draw your loads along. A consequence here is that you do not get some torsional results as easily if you use this option, but it's very fast and effective. If you, as in my case, you have a slab and you want to get some depth for your traffic loads, then the railway option is the way to go. So let's use that one today. And actually today, the goal is to set up 2 railways on the same bridge. And to do that, we have to start by going into the default settings option. If I were to start drawing right now, then the default setting is set to just 1 railway. So if I start to draw right away, then I'm limited to just 1 railway. So we have to go in here and into our options first. We can start in the general tab. We can keep the names here unchanged for now. I'm interested in this example. I think the MY results for bars is fine, as well as the MX for shells. And let's not use any simultaneous results as we want to keep the analysis time down. For load model, since I was already doing some testing here, as you can see, the train model we're going to be using is the LM71 model. It looks like this. So we start with a distributed load, some distance, then we have these 4 250 kilonewton loads, and then there's a distributed load at the end. And as you can see here, the length of these distributed loads can be any length, as it should be. So the setup here is I go to settings and I select this LM71 package, which is this geometry where this means that we can have the LM71 load in the first lane, second lane, third lane, or others lane. So this actually means that the software it can place the load in any lane, but it will only do so in the most critical ones. And since we only have 2 lanes or railways, of course, it can be in maximum 2 lanes. But it doesn't hurt that we have these third and others options. It doesn't affect the calculation for this time. Going into load modifier, this option here on the right, the wheel load ratio between the tracks, something that can be a bit confusing if you're not paying attention the first time you jump in here, is that this is set to 1.25 by default. And this is, of course, based on the Eurocode recommendation for us to account for the lateral displacement of the tracks. So this is baked into the default settings. So let's use this one. And now here we get to finally define the number of railways. So this will specifically limit how many tracks we get to draw. So it's important to get this right from the beginning. Let's go with 2. For calculation options, we will start by using this brute force option with 10 number of positions along the stakeout line. So this is not a very fine level of detail, but I will then use this later on for the sensitivity analysis. So this will probably get us a very fast calculation time right away. Now I click OK, and now it's time to finally draw some loads. I have to start with the stake outline through the center of the bridge. I click enter, And now it's time. You can see here in the bottom left which step you're in. So right now I'm supposed to define a left rail. And since I have two railways, the plan is to have one rail for each grid grid that you can see on the screen right now. So I will go from top to bottom. This will be my left rail, and this will be my right rail, and then this will be my other left rail, and this will be my second right rail. And then when I click enter, we can see that we have generated this kind of load pattern. I've had some visual bugs here lately for the traffic loads, that it doesn't show up immediately. What you can then do is to go over here to the right into display settings, and you can, for example, turn on load value. And now these arrows appear in my model at least. So, so even if I turn this off, I can still have these arrows to indicate my point loads. So this is this is the train load. Next step that is very practical to do, and what always happens when you use the traffic load module, is that for each rail we have now defined a grid or a line pattern in this case. So in the load case list, we get these new load cases where, as usual, every case is a unit load placed into one of these nodes that are defined along the lines of our traffic model. And here we can turn on the load value one more time to see the TLT unit here. And we can also see that these are connected. So we get one up here, and then we get one here, and so on. What I want us to start with is to rename this, because the default naming is a bit confusing, I think. And how you can do that is you simply open up one of these load cases, you right click onto this pattern, and you go to properties. And this will also be key for our later sensitivity analysis. Here you have some options to actually control this grid. First at top, we can select a name. So here I will go with left, since this is the left rail of the left track, so to speak. And here we have some options for the number of nodes that we get. And these nodes are basically the number of positions that will be evaluated for the placement of the traffic load. And you can either go by division number or you can go by distance. For this case, again, just to get this first analysis really simple, I will reduce this to 10 division numbers, and this will mean that I get 11 nodes in total. So let's apply this, and now you can see this is a very coarse analysis, and I get 11 steps in total. So let's repeat this for the other tracks. So here, let's go with left, right, and again we go by 10. And again, it's left mouse button and then properties. So here we go by right, left, again 10 division number, And then on to the last one, properties. Then we go to right. Right, you can of course use any name that you would prefer here. And you don't have to change this name. It's just, I find it a bit confusing, the default way it's set up. Okay, so now we have reduced the level of detail in our calculation. At this point, I think we are ready to, I think we can do, just to show you how that works also. In the last webinar, I showed you the math generation tool. And in that case, I used it if you have several different traffic loads and you want to generate many results at once. But you can also use this tool effectively if you just have one type of traffic load, as we have right now, but you want to get more types of results, because right now you only get the results that we asked for initially. So right now we are only getting the results for bar, the MY plus results for the bar, and we get the MX plus results for the shell. So if we want more results, we have to go into math generation. And here I can go with the load model of the selected load pattern, so the LM71 pattern. And now, as usual, I just select the results that I would like. And we're not really interested in having a lot of results right now, but I wanted to show you how you can use this tool for just one pattern. Let's add these results, for example. So now I will get 6 more traffic load patterns that are copied for this traffic load setup. And as always, these through the math generation, you will generate new load cases in the load group that was selected. And in this case, it's called applied if I just copy the currently selected traffic load. All right, let's go to the meshing. All right, and here you can see I have already generated a mesh. Let's try that one more time, because I want to do it with a 1 meter density. Again, quite coarse for this example, but that's the point. So then you click prepare to apply the mesh. In this case, you can see that the mesh isn't really, it doesn't really go well with the lines that I've drawn my rails along. So what I would like to do in this case is to divide this plate to get some nicer results, I think, for my bridge geometry. So let's go back to structure and let's type in ln, which will bring up the line command. And I will draw some lines, and then I will divide the shell to get some better control over the meshing. So I will simply draw some lines where our rails are. Like this and like this. So 4 lines. Now you can find on the left side, it's a tool called modify region, which applies to our shell element. So you go in here and then you can select the split region alternative. And now you simply select your shell, and then we can use this option, maybe, no? Okay, predefined lines. Then I get to pick my line, and now you can see the shell has been divided. So let's keep going with this method. Now we have 5 different segments of our shell. Let's go back to the finite element mesh. Let's again apply a 1 meter sized mesh like this. And now you can see it fits nicely onto our rail path. Let's go into analysis and let's run the load cases. And as you would usually want to do for the traffic load module is to go with the maximum of load groups alternative. For now, let's just do some load cases calculation. Okay, 11 seconds. Now I want to show you a few nice tips on how you can view your results in a clear way. Let's, for example, go over here on the right side to results. Let's look at bar internal forces, My, and I can pick my, was it test, we call it, I think, graph. And here you can see the results appearing. Yeah, and now I've already done this, but the way that I get these results to appear in the model is through the automatic numeric values option, which is a really nice tool. Here you can choose to add either local maximum and minimum results or just global maximum and minimum results. So right now we are looking at local maximum results for these beams due to the traffic load. If I went with local maximum and minimum, you can see there's several results that get added. To keep it a bit more clean, you can also just go with the global maximum and minimum results. And the same applies for the shell results, of course. You see we have a maximum bending moment in the middle of the longest span, so that seems reasonable. Another nice tool with this result with the automatic values is that it shows you where the maximum result is. And if you've seen my previous webinars, you know that this can be very useful if you're interested in using this generate load cases by pattern tool, which is the way where we can cover our structure and get results or get the traffic load geometry that generates the maximum result where we are currently hovering. So then it's very nice if we can directly see where the maximum result appear. So in this case, I could simply I would click in this node, and then I will generate the static load case that you can see for the traffic load on my screen right now, and I can do a nonlinear analysis or load combination using this geometry. I think that was pretty much what I wanted to show you for this result, or for this first example. Maybe we can find some more interesting results. But let's move into the second part then. That is I think the most interesting one, the sensitivity analysis. Because the tools are not that obvious, I think, for the 3D Bridge module. Generally, when we think about sensitivity analysis, you probably think about the mesh. And this is true for this case, but we have some other tools that are really relevant for this kind of analysis. And here you can see, if I go back to my load cases, I now have this static setup for, and it shows you also the exact position that it was, where it was optimizing the results, so to speak. But for the sensitivity analysis for traffic loads, we have, for example, in the calculation options, we get to choose the search algorithm type as well as the number of positions or restarts that are used during evaluation. This can have a huge effect on the level of detail and on the time. So let's do some testing with this one soon. And another choice that has a big impact on this is the option that I showed you previously. This moving load grid node options. The number here that you use has a big impact on the results and on the time it takes to calculate. So first, I want us to do, because a key to remember when you're using the 3D Bridge module, and especially the math generation, when you're generating many results, for example, several hundred types of traffic loads, it is not uncommon for a calculation. If you run the analysis for just one traffic load result, in theory, how this works is that you can multiply the runtime for that one result with the total number of results that you're going to be asking for in your final run, let's say. So that time is linear. I don't think it's quite that simple, because different types of analyses, if you have a surface load, for example, that is more complex than an axle load. But I think an easy way to do an estimation is to think of it like this. You multiply the runtime of one result by your total number of cases, and you can estimate the total runtime you will have in the end. So when you optimize for your running time, you should use just one load case, and you should play around with the mesh. You can play around with the fineness of the optimization algorithm and also these grid options. So that's what I'm going to be showing you for the rest of the webinar. And I think it's a good way to work is to use Excel, for example, and we can create these nice plots of runtime versus some key result that we might be interested in. So in my case, yeah, now we have to rerun the analysis because we added a load case. But my goal here will be to run the analysis one more time with just one load case. I will look at bar results, MY, and I will look at the maximum moment results that will appear somewhere here, and then I will compare that for different types of graphs. So let's tidy up in here a bit. Let's just keep the test for now, since it includes the beam result. Or what we could also do is to, maybe this is the most obvious one. We can go to mass generation, and now I can just ask for specifically that result. So that's what I'm going to do. So I'm going to be using the bar my plus maximization. So now this result has appeared here. So let's erase all the other ones. Like this. We can even remove the test one here also. We can use, and we can also remove this. This is the one that was created on this generate tool in the results. And it's nice, it gives you, it shows you what has been optimized. So here it was the shells result for MX that was optimized, but let's remove it for now. So now we only have the beam MY result. And then of course we have these are the unit load cases in the grids, which needs to remain. So let's just double check our settings here. Brute force and 10. Okay, let's go. Okay, so 7 seconds. I will create a row here for time, and I will create a row for result. Let's add MY. And then I have a base result where I'm using 1 meter, or I'm using a 1 meter mesh. I'm using 11 load steps. I'm using the brute force 10 option. So this will be my base case that I will be comparing results to. So for time, let's add let's add 7 seconds in here. And now let's go to our results. Let's look at bar internal forces MY. Here we go. Okay, so 470.3. And now it's time to just play around a bit. And the things we will try and change are the mesh size, and we will change the step number, and we will change the algo type, we can say. So let's start and look at mesh sizes now. Let's reduce this by half, for example. And then we apply with the prepare command. And now you can see we have a much, much finer mesh. And now we just see what results we get if we run it. Hopefully it won't take too long. Eight seconds, not too bad. So let's copy this down here, and now we can write 8 seconds here. So this is for mesh 0.5. We got 8 seconds, and now let's look at our results. Okay, so 464.6. Let's try something else. Let's see if we can have an even finer mesh, 0.25 size. So now it's a really fine mesh. Fifteen seconds. Mm, 462.5. So as you can see, it's the results are not changing that much. But I think sensitivity analysis is a good exercise because we tend to assume that some changes will have a certain effect on calculation. But I think this will make you see that that's not always the case. Let's move these over here. And let's just copy this down here. The goal will be to make a plot here of how time versus results correlate. But yeah, I don't think the results will change that much if we use an even finer mesh. So let's not do that. Let's instead go to the step number, which I think will be really interesting. And again, we access these through the load case list here. We right click, we go to properties. So I would like to go by distance instead. And as you can see here, the distance previously was 2.6 meters between each node. Let's reduce that quite a bit to 1.5 meters. So then we went up to 19 points in total. So now we have to do the same thing for the other ones. Point 5. Sometimes it's hard to select it. Okay, distance 1.5. And lastly, 1.5. Now we have changed all of these. For the comparison's sake, I want us to swap back the mesh that we were using originally. So let's go back to the 1 meter size mesh. And then we run the analysis yet again. So 8 seconds. Type that in here. So step number, this time it was 19 steps. And again, let's copy this down here. Oh, 19. Yep. Let's look at the results. So 486.4. Oh, here we got quite a big increase in results. Let's see if we can change that even more. Let's use even more steps this time. see. Sometimes these are hard to select. Okay, let's reduce this to 0.75 this time. See how many steps we get this time. Okay, so 36 steps. Yeah, let's try it. So 0.75. I could also, now that I know the number of steps, I could also just type 36 here, and it would give the same. Okay, actually, yeah, I have to minus 1, of course. So 35. Now we get 36 steps. Let's keep going. These are tricky to select. There we go. 35, and the last one. 35. So one more time, let's run the analysis. Uh, 8 seconds. One more time. So that doesn't change the time too much. And this time we have 489.3. Okay. And now let's change the final type. We're going to go into the algorithm settings. But first, I have to change this back, of course, to the original setting for our comparison to work. So the first one was 10. And 10. And 10 steps. And the last one. So to change the algorithm options, the only way to access that is through the traffic load module button here in the loads. We use the question mark. Something to consider is that if you have selected the road vehicle traffic pattern here and you want to change a train vehicle, you're not able to access that load if you have the wrong type selected. So make sure that you select the right type that you're working with right now. So here in calculation options, the thing how it works is that you basically increase these numbers to get more detailed results. And also generally the brute force method is faster and simpler. The multi-start optimization tends to take a bit longer to run, but you will get more accurate results. And now everything I talk about now also, basically, it's worth to mention that it might not work the same for you because every geometry works differently. You might have a really coarse mesh and you might get lucky and you manage to find the maximum value at once. But this is how it generally works. So first, let's increase the number of positions for the brute force method, which will give us more times for the algorithm to look for the critical results. Let's increase this to 25, for example, or 20. And then let's run the analysis again. Another thing to mention with running time in the traffic load module, okay, 7 seconds, is that for these linear calculations, the time tends to be much lower than for the shell type. So that's worth to consider. So we had 7 seconds. Let's copy this down here. 7 seconds, and the result is 478.5. 78.5. Let me see. Here we were using 36 steps, and here we are using the BF20, let's call it. Okay, let's increase this even more now. We go back to the traffic load module, we question mark, we pick our pattern. Let's test it with the multi-start optimization one time. Let's go with multi-start optimization. Yeah, let's increase this to 30. I think for the type of model that I'm running now, in my case, it will probably not make that big of a difference because the model is quite simple for the software to analyze. But in your project, if it's more complex, it might make a huge difference to make these changes. But let's see how it goes. Multi-start, 30 restarts. Yeah, you can see this was even faster somehow. So, or the same time, I should say. So still 7 seconds, and now we got 487.7. So these were all the results that I wanted to create. Now let's make some interesting plots to see if we can find some relationships here. So let's plot this data with a scatter plot like this. And do the same here. And a third time. Yeah, the third one is interesting. So the way that this usually works, as I'm sure you're aware, you are looking at maybe this one is the best example where the chart tends to flatten out. In these charts, we have the calculation time, of course, on the x-axis and the results on the y-axis. And when you increase the level of detail of your calculation beyond a certain point, you tend to the results don't change much eventually, but you can increase the calculation time infinitely because you can always make it more detailed. So how you approach this is, of course, you want to find a good balance here. Maybe this node for this example is a good way to balance. We have an 8-second runtime, and we are getting some better results. But yeah, but this was the mesh one result also, and I think the mesh it probably I don't think it helps the results for the traffic load module as much, since we are working through these other tools instead. You can see both of these analyses, the result is increasing, and it is approaching, let's say, 490 kilonewton meters as a maximum result. So here, yeah, you would generally see the graph going quite rapidly up in the beginning, and then it tends to flatten out towards the end. Now here I had the same calculation time, so you won't really see that effect, but I would guess that generally the curve tends to flatten out. So again, you're looking at a good compromise. And here, of course, I had the same calculation time for all these three. So not a good comparison. What I've learned so far working in the module is that the number of steps tend to be a quite important decision. If you want to increase your level of detail or the accuracy of your results, it could be a very good idea to increase this step number. Yeah, I wished I had a graph to show this better, but I was afraid of too long run times today. But this is a great tool to increase the detail, and it usually doesn't increase the time that much. So I encourage you to test this a bit. And I think the example that I showed you today, where we have railways and we have several railways, that's the most cumbersome example, where you have to change these number of steps several times. But for all of the other traffic load options, you only have to change this once per pattern. So that's more feasible. The type of algorithm and the number of steps, it's a bit harder to judge also. Generally, it works, like I said. The multi-start, you can usually find much more accurate results. And I think you can see here that the accuracy jumped up quite a bit, even though we previously used this brute force method for 20 steps, which is a decent amount. We were still only able to get a good detail once we went over to multi-start. But the multi-start usually takes a bit longer to run. So yeah, I think I won't say too much more about this now. I hope that this was informative. Maybe even if you're not working with bridges also, this is an approach you can use for any project, of course. And again, I think it's important to highlight these very specific tools that we have in FEM-Design in 3D Bridge to really help you be economic with your time. So yeah, thank you to everybody who listened today. I think this is a good time to wrap it up, and thank you also to everybody who is listening to this afterwards. I got some really nice feedback on the last webinar, so that was nice. I hope this can be valuable to you out there. So yeah, thank you for today, and I'll see you next time.